Greetings from Paul Bamberg. This is the preview video for class number 5 in Math S-322. The topic for today is continuity. Now the definition that Ross uses is quite possibly not the one that you may have used in teaching AP Calculus. If you used a definition of continuity at all, I'm told there are plenty of AP courses where continuity is used but never defined. It's a definition of continuity in terms of sequences. Since we're now quite expert with sequences, this definition will make the subject very easy because we can rely on earlier theorems. I found it useful to introduce a couple of phrases in describing this definition. First, let's consider the case where we have in the domain a sequence x sub n that converges to x naught, and in the codomain, the sequence of function values f of x sub n converges to f of x naught. I'm going to refer to that sequence as a good sequence. A good sequence means that f evaluated on the limit is equal to the limit of the function values. However, it's possible to have a case where the sequence x sub n converges to x naught. The function f can be evaluated on all the xn's. It can be evaluated on x naught, but if you take f of x sub n and form the limit of that sequence, it's different from f of x naught. I'm going to refer in that case to the sequence x sub n as a bad sequence. Once you've got these definitions, it's easy to define continuity. The statement function f is continuous at x naught means simply every sequence is a good sequence, or equivalently, there are no bad sequences. Now that's not the only way of defining continuity, and in fact the more conventional definition is the epsilon delta definition of continuity. It basically says if you want to make the function value close to the value at x naught, all you have to do is go far enough along in the sequence so that you make x sub n nice and close to x naught. Let me be precise about this. F is a real valued function with some domain in the real numbers, and if I pick some point in the domain x naught, f is continuous there if and only if the following condition holds. You challenge me to make the function value close to f of x naught by specifying a positive number epsilon. I respond with a positive number delta, and I win if for any x in the domain that is within delta of x naught, the function value at that x is within epsilon of f of x naught. This definition is equivalent to the no bad sequence definition. That's something we're going to have to prove, of course. Both these definitions are useful. If you're trying to prove that a function is continuous, which means you have to show that every sequence is good, it's sometimes easier to use the second version of the definition. You start with an epsilon, and then you find some delta that does the job. And I say a delta, not the delta, because there are many different deltas that may work. If delta equals 1/1000th works, delta equals 1/2000th will work equally well. However, in talking about limits of sequences, we found that there are lots of cases where, although you can do a formal proof of the limit using epsilon and finding a capital N, it's frequently much more efficient to use all the limit theorems that we've proved, and the same thing is true for continuity. If you're trying to prove that a function is discontinuous, the no bad sequence definition is the way to go, because all you have to do is construct one bad sequence. Armed with this definition, we can prove lots of useful theorems. First one, if a function f is continuous at x0, then so is its absolute value. By the way, the converse of this statement is not true. Think of the function that is -1 for negative numbers, +1 for 0 or positive numbers. That function is definitely discontinuous at 0, but its absolute value is the constant function 1, which is continuous. If you have a continuous function f and multiply it by a real number k, the result's another continuous function. If you have continuous functions f and g, then their sum, f plus g, is continuous. And you may already be able to visualize how the sequence definition of continuity is going to pay off here, because we've already proved that the limit of the sum of two sequences is the sum of their limits. Similarly, we can prove by using a limit theorem that if you've got two continuous functions f and g, their product is continuous. And it works for quotients too, as long as we're a little bit careful. We have to say, of course, that g of x0 is different from 0. Otherwise, we'd be dividing by 0 and trying to evaluate f over g at x0. And if that condition is satisfied and we have continuous functions f and g, then their quotient f over g is continuous. Finally, the composition of two functions is continuous. This guarantees the continuity of functions like sine of x squared. If f is continuous at x0 and g is continuous at f of x0, that's like x squared is continuous for x equals 2, but the sine function is continuous for its square, 4, then the composite function is continuous. If we prove that the identity function is continuous, that's pretty easy, and the elementary functions of algebra and trigonometry, nth power, nth root, sine, cosine, exponential, logarithm, and so on, then these theorems guarantee basically that if you can write a formula for a function in which there's no risk of dividing by 0 or doing something outrageous like taking the logarithm of a negative number, that function is continuous. And I've actually at Harvard taught a multivariable calculus course in which the textbook used that as its only characterization of continuity. Never bothered to define continuous. This rule actually works pretty well. Now for two wonderful theorems about a continuous function on a closed interval. That's absolutely the best case. This closed interval from A to B is a special example of what more generally is called a compact set, and we can prove two theorems by using the Bolzano-Weierstrass theorem. First, f has to be bounded in this case. On an open interval, a continuous function like 1 over x on an open interval like 0 to 1 doesn't have to be bounded, but if the interval is closed and the function's continuous, it's also bounded. Second, f actually achieves its maximum and minimum value on that interval. They're not just approached as limiting values, they're actually achieved. I think most students of calculus know these results and probably haven't thought about why nobody proved them. The reason you can't prove these in most introductory calculus courses is that the proof requires the Bolzano-Weierstrass theorem, which is itself a little bit tricky to prove. One final theorem, the intermediate value theorem. Everyone knows the intermediate value theorem. It says if you are drawing the graph of a continuous function, it crosses an arbitrary horizontal line, and the proof is the function being continuous means that you have to draw the graph without taking your chalk off the blackboard. But we can do a little bit better than that. let's state the result a bit more formally. We've got a function that's continuous on some interval I, and in this case, the interval I doesn't have to be closed. It could, for example, be the function 1 over x on the interval from 0 to 1 that is open at the 0 end, so that there's no risk of evaluating the function when x equals 0. Here's what the intermediate value theorem says. You've got two numbers, a and b, and a is less than b, and you've got a value y that's in between f of a and f of b. In that case, the intermediate value theorem says there exists an x in the open interval from a to b, not an endpoint at which f of x equals y. Basically, this is a theorem that's useful in proving that a certain equation has a solution. We're going to prove this using the definition of continuity in terms of no bad sequences, and that makes the result quite a bit easier, in my opinion, than the standard proof. Second theorem. The image of an interval is either a single point, that's the case, for example, if you have a constant function, which is certainly continuous, or an interval j. What the theorem is basically saying is that a continuous function cannot map an interval into a pair of disjoint intervals, leaving a gap in the codomain. Next, if you teach AP Calculus and are teaching your students about derivatives of inverse functions, you need this theorem. If f is a strictly increasing function on its domain, it has an inverse function called f inverse that goes from the codomain of f to the domain of x, and that function is strictly increasing as well as continuous. If f is strictly decreasing, it has a continuous, strictly decreasing inverse function. In a week or so, we will prove that if f is differentiable, these inverse functions are differentiable. And in order to do that, we're going to need the fact that the inverse function is continuous. Finally, if you've got a function that is one-to-one on an interval, this happens either because it's strictly increasing or strictly decreasing. Well, this turned out to be a lot shorter than 20 minutes, but I covered all the high spots, and we'll have an interesting time proving a lot of these results in class.